All right, so today we're going to have a look at the fundamental theorem of calculus, and if that sounds important to you, you're absolutely right. It is a very important concept that we'll hopefully look at today. So here it is. What it says is if we've got an integral of a function, we're just calling that f of x at the moment, integral of a function f of x, and we go take that from a all the way to b, that's the same as looking at our function f from b minus f of a. Now, the difference between these f's are the capital F of x is a function such that if you get the derivative of it, it's going to give you that smaller one. All right, so we know this is the antiderivative sign. So basically, if you find the antiderivative of this function, you get the original f function. And if you substitute in that b minus the a, that's our fundamental theorem of calculus. Now, the other way to look at it is if you find the derivative of the antiderivative of a function. Now, this function's in terms of t, we're integrating in terms of dt, but x is our what we're taking it across. Right? If you do this, what we get is we get our original function in there, but it's going to be in terms of x, and we'll have a look at how that works a little bit later on. But this is the second part of the fundamental theorem. If we take the derivative of an antiderivative, it kind of just leaves us with what's in the middle, as long as we're taking it over this x value. So these are a couple of results, and we'll have a look at what these mean in a minute. But basically, if you take the antiderivative of the integral from a to a, so you're not taking it across any length. So remember, this is asking us the antiderivative is asking us to find the area under a curve. So if we have an axis and we've got a curve, find the area under a curve between a starting point and an end point. So here we've got A and A. So our starting point, if we draw another one of these, is A, and our end point is also A. So that's going to give us an equal to 0, and it basically means there's like 0 area under that line because we're not moving anywhere. All right, that's the first part. If we do the derivative from one point to the same point, we get 0, and this is the second part. So basically with this second part, what we get is we're taking an integral from a to b. So if we've got a function and it looks like this, taking an integral from a to b, and we're adding on an integral from b to c. So we're starting at b and we're finishing at c. All right, and we're adding these two things together. So this one plus this one. Now, a way we can simplify that is by saying if we're starting at A and we're going to B and then B to C, we could just go from A all the way through to C. And that's what this second one tells us. Instead of doing this in two parts, we could just go all the way across, get rid of our B and just integrate the whole thing. All right, so those are results of our fundamental theorem. All right, so let's have a look at how we use this to prove some stuff. So first of all, we want to use a fundamental theorem to show that the integral from A to A of f of x dx equals 0. Now, I kind of showed you that, but let's have a look using the theorem. So this is our theorem here. We remember that, let me just put that in here. We remember that, if we take our integral and go from a to b of f of x, it's the same as the integrated function from a to b. So what we're going to do is let's write that out. So I can rewrite this sentence as this part here. So f of a minus. So we start at the top and we minus the bottom, minus f of a. F of a minus f of a. That's the same thing. So I could write that equal to 0. All right, so using our fundamental theorem, that means our rule that I told you existed, that means that holds, which is good. All right, so this next one, we're going to prove that the integral from a to b is the same as the negative of the integral of b to a. So let's have a look at writing. So let's write this first part, so integral of a to b of f of x dx. So we could rewrite that using our formula. We put the top one first, so it becomes capital F of A because that's the top, and the top one goes first, as we can see over here as well. And we subtract f of b. Now, if we're a little bit fancy and we can kind of see what's going on in the future, we can say, if I put a negative out the front, like take the negative out, I can rewrite this as f of b minus f of a. So if I put that negative back in, the f of b becomes negative, which is what we had at the start, and the f of a becomes positive, which is again is what we had at the start. But now I've got it written in a different form. I'm going to leave my negative out the front, but if I've got f of b minus f of a, I can just write that as, so this thing in the brackets, I can write that as the integral from b to a of f of x dx. Now, getting rid of the brackets, I'm just left with my negative b to a of f of x dx, and look, I've proved that this thing equals this thing, which is excellent. Now, there's many versions of things that you can prove like this, but they all basically follow this same general structure. So we'll have a look at these as we move through, but I'm not going to show you any more today. All right, so next I want to use my fundamental theorem of calculus to find the area between the x-axis and this function, y equals negative square root of 4 take x, from 0 to 2. So the first thing I want to do is, my fundamental theorem tells me I need to know the integral of this function. All right, so this function that we've got for y is basically this f of x. So I want to find the capital F of x. So f of x equals the integral of my lowercase one, which is, like I said, negative square root of 4 minus x. Oh, the integral of that dx. I'm going to rewrite that. I'm going to take the negative out of the front because it's not necessary for the integral. I'm going to write 4 minus x to the power of 1/2 dx. All right, so to get the integral of that, what we're going to do is use this formula at the bottom. So we've got something written in this form. It's a bit mixed up, but it is in that form. So if you want to get the integral of that, we leave the negative out the front. We do 1 divided by a, where a is the thing in front of x. So 1 divided by negative 1. We're going to leave our 4 take x as per normal. We're going to add 1 to our power, and we're going to divide by 1 over 2 plus 1. So negative and negative, that becomes a positive, so 1 over 1 is just 1. So this whole thing here just becomes positive 1, so it just goes away. And we're left with 4 minus x to the power of 1 over 2 plus 1 is 3 over 2, divided by 3 over 2. Now, when we divide by a fraction, we can change that to be, bring the 2 to the top, leave the 3 on the bottom, 4 minus x to the power of 3 over 2. All right. Now, this should have plus c on the end as well, but we're not going to worry about plus c because our fundamental theorem doesn't care about that. But we're going to use this term here to work out our solution. So we need to put in this term and start with our b, our top part, so that's 2, and finish with 0. So what this is going to look like is the integral of negative square root 4 minus x from 2 to 0 dx is equal to 2 over 3, 4 minus, we chuck our 2 in, 2 to the power of 3 over 2, subtract 2 over 3, 4 minus 0 to the power of 3 over 2. All right, so that's the fundamental theorem, and now we can just chuck that in a calculator. All right, so this then gives us an answer of 2/3 2 root 2 take 8, or it's like -3 or something. So yeah, you can just put that in your calculator and work it out. So that's just how we use the fundamental theorem in this example. So we're going to have a look at our final example here. We've been given, so we want to find g dash of x given our g of x. So we're going to use our fundamental theorem of calculus as well to work this out. So the first thing I'm going to do is I'm going to write this out a slightly different way. So I'm going to write this as g of x equals the antiderivative from x to 0 of f of x, lowercase. Sorry, f of t, it's currently t is the variable, dt. And that's going to be really important later why I've written it like this. All right, where my f of t is this. Now, if f of t has an antiderivative of f of t, we can use this formula to write out our equation. So g of x equals f of our first term, x, subtract f of 0. Now the original question asked us to find g dash of x, which is going to be equal to f dash of x, take f dash of 0. But because this is 0, it's a constant, so it's just going to go away. Derivative of a constant is just 0. So therefore, g dash of x just equals f dash of x. And we set our antiderivative up here. So this just equals f of x. So therefore, our g dash of x is just equal to our original function, this original one, the power of x minus x. And that's the last type of example we're going to look at. So hopefully we'll have a go at some now, and thank you.